In this video, we are presenting our work, Advancing Player Identification and Tracking with Global ID Fusion. In broadcasting videos like NBA streams, we have a lot of challenges when doing ID-aware tracking. For example, the videos are usually multi-perspective. The players are likely to have different clothing in different games. The zoom changes across the videos with different levels of detail. The players have irregular poses, and uniforms make it difficult to distinguish between different players in their teams. Our work addresses these challenges with three main contributions: MuPNIT and MuPNIT ReID datasets, a multi-perspective benchmark for sports, featuring more than 2 million bounding boxes across 283,000 frames of NBA games, Global ID Fusion Framework, a high-performance online fusion approach for real-time tracking and identification, and lastly, identity consistency metrics that evaluate tracking stability and provide new insights into identity prediction trade-offs. MuPNIT is a multi-object tracking dataset. We feature it with both 60 and 30 FPS, varied video length, plus multi-perspective and a global ID dictionary. MuPNIT is a challenging ID tracking benchmark with remarkable average reassociation gap and consecutive bounding box change deviation. The former depicts the long gap between the reassociation of the same tracklets. The latter measures the drastic bounding box size changes. MuPNIT ReID is an NBA player re-identification dataset. We created two versions. The full version contains all player crops from MuPNIT. To compare with established ReID benchmarks, we built a light version on top of that, with around 200 images per player. The benchmark has special features like text descriptions, uniform, and irregular poses.
Let me walk you through our idea of identity tracking, and let's assume we have a broadcast video with different cameras, camera angles, and scales. At any point in time, we might be looking at a different camera stream, depending on the action that is unfolding. That makes tracking the different identities present in the broadcast difficult using a regular frame-by-frame tracker, as in the best case, different camera angles give different identities to the same person. This is because motion trackers rely on bounding box overlap between frames, so if there is no overlap, or the bounding box drastically changes its size, the tracking fails. This also applies to motion tracking systems that utilize ReID modules. The reason for that is the lack of global feature space by which they can be linked. There are offline methods that improve tracking, but they require a second pass through the stream to create clusters of features that can link the identities. To simulate the offline method, let's assume we know who likely is present in the video. In this case, we have Klay Thompson, Kevin Durant, and Kevin Looney. We can provide the model the information about these players, like an image or text describing the player in a form of a global identity vector, which we can look at as centroids for all player feature clusters. This enables us to identify and re-identify people across the different views, no matter the camera angle. How does it work in practice? We start with a traditional motion tracking system that matches bounding boxes across the frames. Next, we add our global identity tracking module on top of the motion tracker to assign the incoming detections to a global identity and thus reducing the amount of tracklets generated. Our ID module takes in the bounding boxes, extracts the crops, and transforms them into feature vectors. These vectors are then compared with our global identity features like images, text, or both, taken from our prior. At each frame and tracklet, we assign a certain global identity. Whenever motion tracking fails to assign a bounding box to a tracklet, right before a new tracklet would be created, we compare the crop with the majority predicted ID in the tracklets that have not yet been assigned a bounding box from the current frame. If we have a match, we assign the bounding box to that tracklet. If not, only then a new tracklet is created. Let's look at an example and assume we get a stream of detections from our backbone. Our motion tracker frame by frame assigns the detections to some local identity, a tracklet. With each bounding box added to the tracklet, we extract the visual features and classify the person with a global identity. When the motion tracking fails, we take the majority global ID prediction for each unassigned tracklet and compare it against the incoming global identity. Once the matching succeeds, we assign the bounding box to that tracklet and continue motion tracking. To measure the performance of our system, we introduce 5 metrics that reveal the performance of our identification mechanism. Frames to first ID measures how quickly we get any type of class for a tracklet. Frames to first correct ID measures how quickly we get a correct classification for each tracklet. Average class switches measures the amount of class switches within each tracklet. Mean correct ratio measures the ratio of correct matches over time. And lastly, MAP measures the precision of the ID classification.
Here comes the result part. First, we benchmarked our MuPNIT ReID Lite with different ReID frameworks. Among them, Clip Family and AP3D stand out. We can see from the activation maps that they effectively focus on distinguishable human representations, motivating our MOT plus ReID selection. To investigate the facial features for performance in ReID retrieval, we additionally report a face-based ReID method using inside face, which fails mainly because of the low face visibility in MuPNIT ReID. As MuPNIT is a tracking dataset, we benchmark MuPNIT with existing tracking frameworks. We added the Clip and AP3D ID modules to the strongest tracking baseline, OC sort, and observed non-trivial gains across most of the metrics. With the integration of global linking, the tracking performance increases. We see additional performance gains when utilizing temporal feature aggregation window. In global context, where we match tracklets with all the player IDs, the ID tracking performance is relatively insensitive to window size. In game context, where we match the tracklets with players that are present in the game, increasing window size benefits the performance in a non-monotonic way. We also noticed that the assignment strategy affects the accuracy, where linear assignment consistently outperforms direct matching.
To see if our method can generalize to other datasets, we have performed tests on MuPNIT, SportsMod, and SoccerNet using 500 generic text descriptions to act as our centroids. These descriptions use 5 most common jersey colors and numbers between 0 and 99. For metrics, we use the standard MOT metrics. Adding these generic descriptions to MuPNIT results in performance improvement across metrics, improving HOTA performance, but most of all reducing the amount of IDs. We see similar results on SportsMod, where we use the validation dataset, which we split based on the different sports included. The improvements are again mostly visible in the amount of IDs created. SoccerNet is the only dataset that has seen a reduction on HOTA and ASA metrics, which can be explained by the identity separation between the different camera views, as we have not seen a similar performance decrease in football version of SportsMod. In SoccerNet, we see the largest improvement in the amount of IDs we have seen on any tested dataset. To conclude, in this work, we have introduced 2 datasets for multi-perspective ID-aware multi-object tracking. We have developed a tracking system that can connect tracklets across different views, and we have introduced 5 global ID tracking metrics to help with evaluation on our dataset. Thank you.